Good morning, pre-calculus. Guess what? We get to look at chapter 12 today, and what we're going to look at is the first three sections of chapter 12, which gives us a little bit of an introduction to calculus. This is for the students who are going to be taking calculus next year. So let's start off with section 12.1. So section 12-1 gives us an introduction to something called limits. Now again, this is very crucial in the area of calculus. And I'm not going to go into too much detail on that. That will be shared a little bit more when you get into the class on calculus. So, section 12-1, our question is this: how do you estimate limits? How do you use properties of limits? And how do you evaluate limits by direct substitution? Now again, I'm going to show all three of these. Again, they're very applicational, especially when it gets into the area of calculus. So, introduction to limits. That's what we're going to do today. First things first is we got to know what a limit is, and that's on page 852. And a couple of bullet points just to share with you. The notion or the thought of a limit of a function is fundamental to all calculus, because calculus really tackles two problems that everything before calculus can't answer. Okay, and I'll hang on to that thought until you get into calculus. So, the limit of a function is fundamental to all calculus. All right, now I have written something down here. I'd like you to take your time to do that. Gives you guys a good idea of what they're saying on showing you on page 582 or even on page 583. Again, I'll let you guys do that. Can't mention this one, just you go ahead and do it. All right, so here is a definition of a limit. And it basically says this: if we have a function, or in this case, remember, if we have function of x, now remember this is the functional value. This is what the y value is. If the y value becomes arbitrarily close to a unique number L, we'll talk about that in a moment, as our value of x gets closer to some value of c, then the limit of the function as x approaches c is L. Now again, this is just a definition of it. Again, the showing of it makes it a little bit clearer. All right, so here's how we're going to write it. This is called a limit. The limit as a value of x approaches c of some function is going to equal L. And again, I'll show some examples. It'll be relatively easy. Now, there are three ways that we can figure out what this L is. Okay? One is by looking at it graphically. I don't have it written here. I'll do it in part of the lesson. We can do it graphically. We can do it by a table. Or probably the most used way you're going to run across is direct substitution. And we'll just hang on to that when we do some examples. So that is what we're going to do today. How do we find a limit of some type of function as a value of x approaches some value of c? All right. Now, here is what they mean by the table form. Using a table to estimate numerically the limit. And then I'm going to show it to you graphically. So again, here's a table. I have the limit of x approaches 3 of this particular function. So again, we're approaching 3. And in a table, we're approaching 3 on either side of x equals 3. Okay? So in other words, I'm going to go and get going from the left side of x equals 3. I'm going to get real close to 3, and I'm going to plug these values into this function. That's where we get these values here. And then we'll go on the other side is 3.1 as we get closer and closer to 3. And this part right here, that's your limit. And again, by observation, we know that our limit is going to be 12. All right, now some of these are going to be very easy to deal with. Some of these are going to take a little bit of time. But we could also have done this same problem. Like I said, we could do this by the table way. We could do it by the graphical way. I'm going to show you that in a second. Or we can do it by direct substitution. Now this one will work great if we're going to do direct substitution. I'm just going to call that DS. It's very simple. You take your x, which we say is approaching 3, and you plug it into the function. So 5 times 3 minus 3. So we have 15, take away 3 gives us 12. Now direct substitution on certain functions works fantastic. Okay, some of them it won't work. You'll see why in a minute. Okay, so if you go back graphically, so I'm going to go y equals. If you look at this function, that's a linear equation. Let's see if they show it on my graph. There it is. There's your function. And what they're asking you is, what is the limit? What is the y? If you go back to this definition here, okay? If our functional value becomes arbitrarily close to a unique number L, as x gets closer to some value of c, then the limit of that function as x approaches c is L. That is what a limit is all about. But if you look at the graph, okay, we look at our diagram, okay, we look here and we got to figure out where x equals 3 is, okay, so we have 1, 2, 3, I'm not doing a very good job here. So in other words, as x approaches 3 from this side and from this side, where does it touch on the line? Well, in this case, it's going to touch on line 12. That's what the limit is. Now, you're probably saying, what's the big deal? Why do we got to need to know this? Well, the limit is important, especially if we want to deal with some of the concepts that calculus is trying to answer. And one of those things that they're trying to answer is, does that value at x equals 3, do we have a slope there? Well, in this case, yes, this one is going to be a straight up the same slope this way. But there are some functions where we're going to say, well, we don't know what that slope is at that point. So we have to just assume that it's going to be that slope. All right, now look at number 2. Number 2, here's another function, okay? The limit as x approaches 0 of our function of x divided by x plus 9 minus 3. Now, what I want to do is first, if we do direct substitution in this problem, in other words, let x become 0 here, we're going to get a statement of 0 divided by 0. Okay? That's what we would call an indeterminate value. We cannot determine it. So in other words, when x becomes 0 on this particular function, we're not going to have a value there. So we have to make a rough guess of, or estimate of what the limit will be. So again, on your graph here, or on your t-graph, or your table, the book uses a table, I'm just going to use a t-graph, it's the same thing. I'm approaching x from the negative side up to 0, and I'm approaching x from the positive side to 0. And plugging these values into this function, we see that our functional value gets very, very, very close to a value of 6. So this tells us the limit at that function will be 6. But the direct substitution says it's undefined. Okay? So remember, this is just an estimate. Let's try another one. I'm not going to show that to you graphically. I'll let you guys do that on your calculator. The next one. The limit as x approaches 2. All right. Well, even in direct substitution here, I'm not really worried about the numerator. Okay, well, that's not important at the moment. But if you look at your denominator, that's 0. We don't know what that is. That's undeterminate. So what we are going to do is define that. Can't use direct substitution in this example, so we have to just go ahead and say, well, we're going to approach x is 2 from the right side of, the left side of the equation, left side of the number line, and approach x from the right side. So as we get closer and closer to 2, we see from our y values it's getting close to 6. All right. Now there's another way of finding out these limits when we learn a little bit more about when we learn a little bit more about derivatives. Okay, so that is what we're talking about as a limit. Now, there are some functions or some limits that are going to fail to exist. In other words, we can't even show them. We can't, they don't exist. It's not going to work. Now, this takes a little bit of practice, a little bit of graphing, which I really want to encourage you to do. And so here is some problems. Do the following limits exist? And here is our first limit. We can do this when we're right off the bat. Direct substitution will tell us it's going to be, in this case, it's going to be 0 divided by 0. So we already know that we have to determine what the limit is. But now the way this function's set up, you really got to get yourself in the habit of graphing your functions, okay? I'm going to clear this. So we have the absolute value. So we go math, absolute value of x minus 1 divided by, and I need to put parentheses around this because I know this is a binomial, of x minus 1. And if we hit graph, that is, if you look at your calculator screen, that is the graph of this function. And this is an example of a problem where the function, again, we cannot find the limit as x approaches 1, because if you go here to the right, okay, as x approaches 1 from the right, we're going to see its 1 value. But if you see here, if we approach x from the left, we get a different value of what L. The top one's going to be 1, the bottom one's going to be -1. That means, in this case, this one fails to exist. However, there's another way of doing this, but we'll worry about that when that time comes. So, since our function of x equals 1, if x equals 1, in other words, the y value of our function is 1 when we let x become greater than 1, and our y value is -1 when our x is less than 1, this limit fails to exist because we're not going to get a specific L. We have to get a unique, its own L. This one we have 2 L's. Doesn't work. Another example. The limit as x approaches 0 of 1 over x. Well, if you go ahead and do direct substitution, that's going to be 1 divided by 0. That's undefined. Once again, if you take this graph and graph it, so 1 divided by x, and graph it, you'll see what it looks like. It looks almost like it's a hyperbola, so to speak, but it's a rational function, excuse me. And you see that as your limit of x approaches 0, we know, well, backing it up, we know that this line right here is the asymptote. It's a vertical asymptote. It's undefined. We can't touch it. So that means this graph never touches the y-axis or goes through the y-axis. So that's why this limit exists. So since our functional value approaches infinity as x gets closer to 0, and our functional value approaches negative infinity as our x is less than 0, you'll see it on the graph. All right, here's another one. Here we have the limit as x approaches 0 of the cosine of 1 over x. Again, if we go ahead and substitute it, it's 1 divided by 0. That's undefined. You can't find the cosine of undefined statement. Go back to your unit circle. You can't do that. So as the function of x, as x approaches 0, the function oscillates between 1 and -1. Well, let's graph that one. Let's see what it looks like. The cosine of 1 divided by x. And let's see, what does it look like? I may have to change something here, okay? See how that looks? As it approaches 0, again, we don't see this here, but if we were to zoom in a little bit more, you get a little bit of an oscillation here. Watch it. It jumps up and down. Again, they don't show it clearly on this calculator, but as it just oscillates a whole lot more in between there. So there is no limit on this function, okay? All right, so that is the first part of the video on the introduction to limits. A very crucial thing, okay? A limit of a function is fundamental to all the calculus. Again, I'd like you to take you the time to read. Go ahead and watch this, okay? I know you guys can do it. It's not very long. He does a good explanation of showing it to you visually. All right, I'm going to stop there, and then we'll go and do another example in the next section, or the second video deals with the properties. All right, guys, thanks.